Hi, and welcome to today's lesson on reasoning and proof. So today we're going to be looking at how to set up a proof for a geometric proof. We hope to give you a nice gentle introduction to how to set up and write a proof today. To begin with, I'd like us to get a definition down for what a proof is. And you can see the definition that I've typed here. A proof is a logical argument of some claim where each step is supported by facts, and that is the truth. In geometry, those facts have to be given information, so given info, theorems, definitions, and properties, algebraic properties that we'll review a little bit today. So a logical argument where each step is supported by a fact. Okay? You have to have a reason for saying that something is so. Before we start to write proofs, we want to learn how to set them up. And so our textbook outlines a 4-step procedure for setting up a proof. We're going to be learning the steps of that procedure, looking at beginning and starting a proof for this statement: the diagonals of a rectangle are congruent. So our first step in the proof writing process is to rephrase the statement as a conditional. And we learned yesterday about conditionals, if-then statements. We want to take this statement and rewrite it, okay, rephrase it in conditional form or in if-then form. Sometimes you have to change the language of these things just a tiny bit to have that work. In this case, we probably are going to want to say something about if a figure is a rectangle, then its diagonals are congruent. So we've got to change the phrasing a little bit to get that if-then statement to set up correctly. So if a figure is a rectangle, then its diagonals are congruent. Okay, so we this helps us. You could think about this as like reading the problem in a story problem, right? We're really looking at the thing that we want to prove, and we're breaking it down into what we can work with. The second step in writing the proof is to identify the hypothesis and the conclusion. Those are important because in a geometric proof, the given is the hypothesis. So this will be the given information. Hypothesis is given. And what we have to prove is the conclusion. So in our example, what we're given is a rectangle. And what we have to prove is that its diagonals are congruent. All right, good. The third step in the proof writing process, sometimes I disagree with this. Sometimes I think this should be the second step. Draw and label a diagram that illustrates what's given. And folks, in this case, what we are given is a rectangle, and we're going to show its diagonals because those are the things that we're looking at. So we're going to draw ourselves a picture. Whoops, not very straight. But it's a rectangle because I say it is. And we want to give it a name so that we can talk about it. I'm going to call mine RECT, rect for rectangle. And what we're interested in are the two diagonals from T to E and from R to C. We draw and label a diagram that illustrates what's given. All right, and then finally, the last step of the setup phase is this. We set up a T-chart to organize statements and reasons. We fill in what's given. Now, folks, we are not going to write a proof today, but we are going to set up what's called a 2-column format. Okay? As we're learning to write proofs in geometry class, the 2-column format is a good one for us. It gives us a way to organize. On the left, we're going to write statements. On the right, we're going to write reasons. And from what we've done already in this setup business, we know the very first statement has to be RECT is a rectangle. What we're given, that's where we start. RECT is a rectangle. The reason we can say that, again, that was the given information. And our setup is complete. Now down the line in this class, we'll add a list of statements and a list of reasons until we get to the bottom statement, which will say the diagonals TE and RC are congruent. We're not about writing them today. We're about setting them up. So if you think about the steps again, we want to make sure that we have our statement, the thing that we're talking about, in if-then form. We do that so that we can identify what's given, that's the hypothesis of the conditional, and what we have to prove, that is its conclusion. The picture, really important part of this, it should show what's given in the problem, and many times I draw the picture towards the top of this process. Finally, setting up that T-chart so that we have a way to organize our information. Let's move on and see if we can't do that for this little example. What it says is any two right angles are congruent, and we are supposed to set up a proof for this. Okay, we're setting up today, not writing. Okay. So the first step said we should rewrite this as a conditional, and I would say pause this video. Let's see if we come up with the same thing. Mine is going to sound something like this. If two angles are right angles, then they are congruent. If two angles are right angles, then they are congruent. All right, there's my if-then. That allows me to begin my proof by saying what's given, two angles. Actually, you know what? I am going to say, I said I often draw the diagram first, and this is a good time. I want to be able to talk about these two angles out there somewhere, so I'm going to start mine with a diagram. I'm going to call my angles H and I. Both of them right angles. See, now when I write the given information, what I'm given is that angle H and angle I are right angles. And what I have to prove, well, that's the conclusion of my if-then statement. Angle H then must be congruent to angle I. And I've done now my first three steps in my setup. I've got my statement in conditional form. I have a diagram that shows the given information, and I have specified what was given and what I have to prove. The remaining thing is to set up that T-chart, and you will see that I very often abbreviate here because I've done this a long time, so sometimes I just write STMT right there and reason over here. And what I'm asking you to do is fill in the first statement. In almost every proof we ever write in geometry class, the given information is what comes first. I'm going to write the reason over there. Now I'm going to write the statement. And what we were given is that the two angles H and I are right angles. All right, we're all set up. Now I'll bet you some of you could think of reasons why they have to be congruent, but we're going to save that for a later time. Today our goal is to set up, and we've done a good job of that. Good. On we go. Okay, as we're starting our proof writing, we've mentioned several times that you can use algebraic properties as reasons in a proof. So we just want to review real quickly for you some of the properties of equality that you learned about in algebra class. A, B, and C are going to stand for real numbers in these things. And the first one says, if A is equal to B, then A plus C equals B plus C. I'm going to write this for a second this way. A equals B is where that started, and here's where it ends. A plus C equals B plus C. What did they do to both sides of that equation? They added C, right? They added the same value to both sides of an equation. Addition property of equality. Addition property of equality. If you just call that addition, I'll know exactly what you mean. And that says you can add the same thing to both sides. Okay? On this one, I don't think we're going to have any mystery there. Instead of adding the same value to both sides, we've subtracted the same value from both sides. This is the subtraction property of equality. Again, it just says if you can subtract something from one side, that's wonderful, as long as you do it to the other side as well. Here we're multiplying both sides by the same number, so the multiplication property. And here we're dividing both sides by the same number, as long as that's not 0. So the division property here. Good. The last one seems fairly straightforward here, but this is an important property in geometry. If A is equal to B, this says, if they have the same value, then B can replace A in any expression. Folks, that is totally true, and it's the substitution property. If they have the same value, then you can substitute one for the other. Sometimes I say swap. Okay, as long as they have the same value, then I can use either one. They mean the same thing. So there's some addition or some properties of equality for us. And let's see. Oh my! I see an equation here. It looks like maybe we're gonna practice our proof writing on an algebraic equation. You had done this probably in your Algebra 1 class. You probably didn't do it a lot, but you have. In a lot of ways, solving an equation, well, it is a logical process. And so we can use solving an equation to help us hone our proof writing skills. And that's what we're going to do today. All right, this says, for example, if 3 times the quantity x minus 2 is equal to 42, then x is equal to 16. We're going to solve that equation. It says we need to supply a reason for each algebraic step. Okay? The given information is the hypothesis, and that's what we said here. What we have to prove is the conclusion. That's where we have to get. And you can see that some of the elements of this have been added in here already. That very first one, though, is just a restatement of what was given. And as we said, very often in geometry class, the given information is the first step. Now, I'm going to ask you to think about this. Forget about the reasons column over here. If you were going to solve this equation, what's the first thing that you would do? I'll bet you that many of you are saying, I'd distribute, and you'd be right. Okay? The first thing we're going to do is apply the distributive property. And that means that that 3 gets sent to both places in the parenthesis. 3 times x, 3 times 2, and there was a minus in there. 3x minus 6 equals 42. I want you to take notice. This reason says why this exists, right? Or you can think, this tells me the next thing I have to do in the equation. So as you look at this one, I hope you're thinking, the next thing I have to do if I'm solving for x, I probably want to add 6 to both sides because I need to get x by itself. And look what this step shows. 3x minus 6, which is what we had, plus 6, equals 42 plus 6. Folks, they added the same thing to both sides, or they applied the addition property of equality. Our next step, now look at this, minus 6 plus 6 is gone. because that's a 0. And 42 plus 6 is that 48. So really what we've done here is we did the work. What we've done basically is said that negative 6 plus 6 is the same as 0. Or we've substituted a plus 0 for those things. We've said that 42 plus 6 is the same thing as 48, so we substituted a 48 for that. Folks, this is a substitution step. You could also here say that you're doing the work or you're combining like terms, and I would totally understand that, but technically it is a substitution. Now in the next step, step 5, they're giving us a clue because they're saying the reason is the division property, and I think to myself the division property is the one that said you can divide both sides of an equation by the same value. So that must be what they want us to write here. That is 3x divided by 3 is the same as 48 divided by 3. That's applying the division property, which says divide both sides by the same thing, the same value. Finally, now, doing the work. 3x divided by 3 is the same thing as just x. We're substituting again here, folks, are doing the work. 48 divided by 3 is 16, and we're substituting a 16 in place of that 48 over 3. So technically that's a substitution step. But if you said do the work, I would know exactly what you mean, and there you go. We've done our algebraic proof, very similar to things that you would have done last year. We gave a reason for each step, and those reasons have to be given information, properties, definitions, theorems. Since this was algebra, the properties, of course, are the most important ones. So very good. Let's see what else is in here. Oh, another one. We're supposed to set this one up on our own. You know I'm going to say, let's pause this video and see if we get the same thing. All right. We have it in conditional form. We are supposed to write out the given information. And the given information is a restatement of the equation. 3x plus 5 all over 2 equals 7. What we have to prove, or what we should get to at the end, is that that only is true if x is 3. We're going to set up a t-chart. There is no picture for this, so we can't really write a diagram for this. Statements are going to go on the left side, reasons on the right. And our first statement should be a restatement of what was given. 3x plus 5 all over 2 equals 7. And we know that's true because they told us. Some folks label their steps and reasons. I'll tell you, I don't always do that, but I will today just for clarity. The first thing that I would do if I were solving this equation is multiply both sides by 2. So I would say I need to apply the multiplication problem or property. That is, I'm going to multiply both sides by 2. 3x plus 5 over 2 multiplied by 2 is equal to 7 multiplied by 2, and that's the multiplication property. Doing the work is the substitution step, and 2 divided by 2 is 1. So 1 times 3x plus 5, or just 3x plus 5. 2 times 7 is 14. Substitution. Great, you're doing great. The next thing we want to do is subtract 5 from both sides, and I want to tell you there are many people who do not write this as 2 separate steps, who instead would just show what they're doing and then make the 4th step be the result of that. That is 3x equals 9, and call that the subtraction property. I must tell you folks, that's probably the way I would write this. I very often do not show the work this way and complete the work this way. It's much more likely for me to do this. The next step in solving this equation would be to divide by 3 on both sides, and that will get me to x equals 3. And the work that I did was divide both sides by the same value. So that's the division property. I want to check and make sure that this, where I ended up, is the same thing as where I was supposed to end up. And it is. So we proved that guy in 2 columns. Way to go. Alright, we are going to try one problem here that has a little bit of a geometric connection. After all, this is geometry class. And we have a diagram drawn. So let's look at what we're supposed to show and what we have given. What we are supposed to show is that AC from here to here, A to C, is the same as B to D, here to here. And that's assuming that AB, this little part, is the same length as CD. See how they're marked there? Okay. So this is really our statement that we want to prove. The conditional would be if AB equals CD, then AC equals BD. Are you with me? All right. The given information then is that AB is equal to CD, and that's already been pictured on our diagram, so I'm going to say that's good. What we have to prove is that AC has the same length as BD, and my hint to you, plan. Don't just start writing plan. So think about this, folks. If I want to get to say that A to C right here, well, just looking at it, that's made up of 2 pieces of segment, right? From A to B and B to C. Those things combine to give us AC. If we look down on the other end, the same thing is true. We've got BD is the segment we're interested in, but we can show it as 2 parts, BC plus CD. And we know that this is the same on both ends. This must be the same as itself. So I think that we are on our way to having a way to write this proof. Let's see if we can work it out here. The very first statement is almost always to repeat the given information. So AB equals CD, and that was given. And let's look at the statement that this person wrote. Oh yes, AB plus BC. That's here plus here. AB plus BC equals CD plus BC. Yep. And folks, look at what's been done. Didn't they add the same thing to both sides? They add the length of BC. That is the addition property of algebra. You're adding the same value to both sides of an equation. Now, this, whoever wrote this, didn't mean angle addition. They meant segment addition, because we're not looking at any angles. We're looking at segments. But by segment addition, that's a postulate. We said it was a common sense postulate that said when you add the 2 pieces of a segment, you get the length of the whole. So AB plus BC equals A to C, and that is true, segment addition. They left us one to write. We have the AC part of it. I'm thinking that we need to go after the BD part of it. So let's do the same thing here. CD, or maybe we should write the BC first. I guess it doesn't matter. BC plus CD. BC plus CD equals BD. Are you with me right there? That's a segment addition. Okay, we added the 2 pieces of a segment, said that that's the same thing as the whole length. And look, folks, right here, AB plus BC, that's the same as that, isn't it? And we said that AC had that same value. We could replace that AB plus BC with that AC. Because they have the same value, our statement says it. Folks, we're substituting this AC in place of that side of the equation. This side said CD plus BC, and that's what we have right there. We know that that's the same as B to D. So we're going to replace that business with that. AC equals BD. And folks, that is a substitution. We swapped in equal pieces. Substitution. And you wrote a little geometric proof. Really, it used algebra properties, but it is about a geometry thing, and I'm really happy about that because that means we've written our first geometric proof. Congratulations. I would ask you to look at that U-Try tonight, okay? And we'll have plenty to talk about in the next class period. So have a good night.